it's a constant. Well, at any rate, let's see what such a function, capital L of x, must look like. I'm going to utilize both the differential calculus approach and the integral calculus approach. By differential calculus, assuming that y equals L of x, what do we know about the function y? By definition, we've defined it to be that function whose derivative is 1 over x. So we know its derivative is 1 over x. The next point is that knowing that y prime is 1 over x, and even though we can't integrate 1 over x, we can certainly differentiate 1 over x. We can now differentiate 1 over x. The derivative of 1 over x is minus 1 over x squared, and we find that y double prime is minus 1 over x squared. By the way, we should observe that we must shy away from x equaling 0, because you see we would have a 0 denominator in that case. If we think of most physical situations, notice that when you talk about the amount, the rate of change is proportional to the amount present. From a physical point of view, the amount present can't be negative. So let's put the restriction on here that the domain of L will be all positive numbers. Okay? Now, here's the interesting thing. Intuitively, I can now visualize how the function L of x must look. Namely, since its first derivative is 1 over x and x is greater than 0, that tells me that the curve is always rising. And secondly, since 1 over x squared is always positive, minus 1 over x squared is always negative, that tells me that my curve is always spilling water. In essence, then, what must the curve do? The curve must be rising, but spilling water. In other words, the curve L of x belongs to this particular family. Notice that once we have one curve, which we call y equals L of x, by any displacement parallel to vertical displacement, we get what? A member called y equals L of x plus c. All that changes is what? The point at which the curve crosses the x-axis. But whichever member of the family we pick, what typifies L of x? Its derivative is 1 over x. In other words, somehow or other, we visualize that L of x exists, and its graph is something like this. Okay? Now, suppose we want a more tangible form, namely, how do you compute L of x for a given x? I thought what might be a nice review now is to see how we can use our integral calculus approach